Our next speaker is one of our invited speakers, Chris Phillips from Edinburgh University, and he will be talking about factorial switching linear dynamical systems and its applications.
Thanks, and thanks to the organizers for the invitation to come here. So this talk is probably less about theory and much more about practice of the use of time series models in condition monitoring. So the situation that we were interested in, and sorry, I should have actually just let me highlight before we get there that this is joint work with John Quinn, who was my PhD student, graduated last year, and also Neil McIntosh, who was Professor of Child Life and Health at Edinburgh and just recently retired, but still active. So the problem is that we may have premature babies in the neonatal intensive care unit. And what happens is that they have, as you can see, a lot of instrumentation on them. And we want to monitor, so if we look at a cot-side monitor, we might say a whole bunch of traces of various heart rate, blood pressure, temperatures, and so on. And really our question is, how well is the baby? That's the key question that clinicians are interested in. The problem is that there's a lot of things that sort of go wrong in a lot of things that corrupt these measurements and make it difficult to really understand how well the baby is. And there are things like maybe there's some probe that's attached to the infant and that falls off, and you could say, well, an engineering solution is to stick the probe on better, but bear in mind this is a very premature baby. It's it's not a very robust organism, and so you want to be a bit careful about that. Also, there are nursing interventions, and these give rise to, they sort of mess up the traces as well. And so really what we want to do is to try to sort of do smart alarming. We want to say really what's going on with the baby, despite all the fact we've got a lot of artifact in the traces. And we'll see an example of the kind of problems we might have with a baby, but let's just talk about the overview. So first of all, I want to talk about these various factors that could affect the infant, or at least affect our model. Get rid of this. So these are the things, essentially different kinds of artifact processes or different kinds of physiological processes that could affect the traces. Those will be put together into a factorial switching Kalman filter. And one of the actual important things about this is that there's a number of these different factors, and in fact we really need kind of knowledge engineering approaches to really say how these different factors will affect the different observations. And that's one of the interesting things we had to do. We can't use kind of generic models about how these different factors may combine. We actually need to use kind of specific models that relate to the domain. So given that, we're going to do inference, and in fact our inference is going to be fairly standard. We're not going to do anything particularly fancy. We also need to talk a bit about parameter estimation in this model. I'll show you some results, and one of the other things that we also did is the stuff I'm going to talk about first talks about the idea that we might have some known set of factors that cause these problems, but really in reality things, the sort of the none of the above category can happen. Suddenly some unknown some factor we haven't modeled may come into play, so, or some particular kind of problem with the infant may arise. And essentially, if you just have a finite set of known factors, you're saying it's some combination of these factors, and it can't handle a none of the above. So that's the last bullet point here, how we handle novel regimes. So in terms of the baby, in terms of the infant, there are heart rate monitors, ECG, arterial line for blood, pulse oximetry, temperature probes, and some transcutaneous probe which measures oxygen and CO2. So these are the kinds of probes that we might have. And we might also have additional things like we might have instrumentation. These babies are in incubators. We might have instrumentation to tell us whether the incubator is open or not, because that's actually quite a useful clue if the nurse is going in there and making some interventions if the incubator is open. Then there are these factors. An example of the kind of, we might have this systolic and diastolic blood pressure tracers. These are measured through the arterial line, and they're bobbling along happily, and then suddenly there's actually something happening here when they're taking a blood sample, and this means in fact that they turn a tap in the arterial line, and the pump now pumps against essentially this closed tap, and you get these ramps that appear in these signals. This is very characteristic of a blood sample. You're seeing these ramps in the blood pressures, and we don't really want to say, oh, help, I think the baby's in real trouble here. We basically want to know that, yes, we can pick this out as a pattern which arises from the taking of a blood sample. And that's some of the kinds of things that we want to do. We want to learn, we want to understand how these are working. There are other examples about something called transcutaneous probe recalibration, where that gas probe, the oxygen and CO2, has to be recalibrated. And there's a sort of stereotypical sequence of events that happen when that happens. You can see the oxygen level, say, I think that goes down to 0, then it goes up to a high level. They basically immerse it in some different solutions. So there are a number of stereotypical patterns that can arise. These are artifactual ones, but this one, bradycardia, is a physiological one. It says bradycardia is about a heart rate slowing down. So we see this plot against time of the heart rate slowing down and then picking up again. And this is a big problem in premature inference. And this is the kind of thing we really want to know about, right? We don't care too much about knowing that some probe is fallen off. We should worry about that. We should go along and reattach it, but we care much more if there's a problem with the baby that may require a rapid intervention by the staff. That's really the whole point of this thing. So bradycardia is an example of a physiological factor in operation, and we want to detect those. So what does the model look like for this kind of data? Okay, we have the observations. These are, say, 6 or 7 dimensional vectors. Basically, our model is a switching common filter. So if you just ignored all this stuff, this is just a common filter. It's saying that we've got the state, the true underlying values of those heart rate, blood pressure, and so on, those vital signs, and that gives rise to the observations. This is just a common filter. Therefore, for technical reasons, we need to have some artifactual state. I'll show you an example later where that applies. But really the whole point of this is that there are also a bunch of discrete factors, and they say things like, is the bradycardia happening or not? Is this probe disconnected? Are we taking a blood sample or something like this? So basically, there are a bunch of these factors. I've just drawn 2, but you can think of having, say, of order 10. That's the kind of structure that we have, and we really want to do inference. We want to do filtering in this kind of model. Mm-hmm. Yep. Okay, yeah, sorry. So this is a linear dynamical system. Yeah, conditional on these, we're going to model this by a linear dynamical system. Well, switching because we'll want to switch, depending on the setting of these discrete factors, we'll switch between different modes of operation. And yes, that's, I'll show you a bit more notation about that in a minute. Okay, but feel free to interrupt, that's good anyway. So thanks for reminding me of that. So this is the kind of model, and just to get some notation, S of t is the switch variable, which is the cross product of all the different factor settings. So clearly, one of the things we really want to be able to handle is that, that multiple things could be going on at the same time. A blood sample is occurring, and there's a TCP recalibration and so on. So basically, we need to be able to have a bunch of bits, or a bunch of discrete variables, and S of t is just the cross product of that state. X of t is the continuous hidden state, and so we basically believe that we can model, given a setting of S of t, we believe that a linear dynamical system is adequate to model what's going on. If it weren't adequate, then we can actually kind of break up each regime into a number of different regimes, but we haven't needed to do that. And then the Y's are observations. So then, this is really sort of common filtering 101. This is the I'm sure we've seen these many times already over the last 2 days. This is the system, the top equation is the system equation, how that evolves, and the bottom equation is just the observation equation. So this is very simple. We know about this. And really what's happening here is that in general, how is that discrete setting going to affect things? It can affect things in a lot of ways. It can affect the transition matrix here, the kind of noise we get, the observation transition matrix, observation matrix, and also the covariance of that noise. So in general, all of these things could be affected. And really, one of the things that's sort of what I want to tell you about is how we actually structure these kinds of things for different for the different switch settings. Let me just say a bit more about factor interactions, because this is really part of the sort of knowledge engineering aspect. We might have a bunch of different factors up here in grey at the top, and we've got a bunch of these observation channels that we're measuring, heart rate, blood pressure, and so on. If we just have a bradycardia, we know that affects the heart rate, so we'll see a drop in heart rate. And basically, the other channels will, at least to a first approximation, they won't be affected by this heart rate thing. They'll just carry on as normal, at least for short times. Alternatively, if we have a blood sample, in fact, that's going to mess up. We saw already that it affects the systolic and the diastolic blood pressures, and in fact, just through the way that the heart rate is computed, based on the arterial line, in fact, the heart rate actually is not computable. It's not observed when we actually are having a blood sample, because we're not looking at the pulse from the baby. We're looking at these. That we don't see that. So we know that the blood sample can affect various channels as well. And the question is really, well, what happens when both of them are active? How is that going to affect things? Well, it turns out here, again, there's some specific physics of the situation, which is that really, because I already said that when we're taking a blood sample, we can't actually observe the heart rate, then the fact that if there was a bradycardia occurring, basically we wouldn't see it because we have a dropout in the heart rate due to this combination, or due to the blood sample. So, but the point of this illustration is that in fact that various of these factors can affect various channels, and they can also affect them in various ways. So what we need to build into the system is this knowledge of how that happens, and this is relatively easy to elicit from the clinical staff. So just to say a little bit more about that, in fact, one quite convenient way to think about this is that if we consider these are the different channels that we're monitoring, and these are the different factors, then we can think of them as having a partial order. For example, if we pick systolic blood pressure, basically if it's disconnected, well, we're not going to see it, and that's the dropout. If the blood sample, we're not going to see we're going to be affecting that thing, and similarly, if other factors are operating, then these will be affected. So we can actually order these in a way. So the problem is, of course, that otherwise, that if we've got this set of factors, and we have to basically have some model for this system dynamics and also observation matrix here, conditional on all those different factor settings, if we had to kind of learn those for each combination, and there could be, unfortunately, that we don't often observe very unpleasant combinations when a lot of things go wrong at the same time, this would be very difficult. So the fact that we can structure this and actually understand how these things work is actually very important for actually building this system. Is that clear? Okay. So let me just say something about related work. Clearly, switching linear dynamical systems have been around for quite a long time. And there are various work in things like condition monitoring or fault detection, so some work by De Freitas et al., and, well, in a wide variety of different contexts. We are aware of okay, yes, good, didn't forget that one. Okay, we're aware of a two-factor factorial switching Kalman filter used for speech recognition by Ma and Deng, and also some recent work by Chemgil et al. On musical transcription. But as far as we're aware, this is the first time this kind of model has been used for condition monitoring in intensive care units. So that's the model. What we want to do is to compute with it. We want to do, and our goal, certainly in the clinical context, is to do filtering. We want to figure out the switch state, S of t, and that's really the most important thing, but it may be convenient also to have x of t at the same time, given the observations from times 1 up to t. Basically, we know that this is a factorial switching, this is a switching Kalman filter, and exact inference is intractable. There are a bunch of things that we could do. We're actually going to do something fairly simple, the Gaussian sum approximation due to Alsbach and Sorensen. Although certainly one could also do things like Rao-Blackwell-Eyes particle filtering. So just to remind you, the Gaussian sum approximation is basically if we enumerate those different switch states at time t minus 1, and basically we figure out, and they have some distributions, there'll be Gaussian distributions at each of those, conditional on those different switch settings, then when we transition to a new switch setting at time t, basically what we're going to have to do is to take all these Gaussians and kind of collapse them back into one. And there are obviously various more fancy things one can do, but this is actually, we've also compared against Rao-Blackwell-Eyes particle filter, and I'll give you some results later, but I think that we've actually found that certainly for our application, the Gaussian sum approximation has actually been effective. I need to say a little bit more about the way that we've actually learned the various dynamical systems and so on. One important thing is actually that we are learning these as, so xi of t is, say, one of those channels. It's like a model, say, for the core temperature of the baby. So one thing we're actually doing here is we're just using univariate models. So although there is this x of t, and we could in general have some matrix of the state transition matrix, we're actually going to use we're just going to model these as univariate series. That has some advantages when we come to issues like, for example, we may want to marginalize out certain channels if we're not observing them, and so on, and then it's actually much easier to do like this. And also the fact that certain switch variables will only affect certain channels means that we can really just concentrate on how the effect of that factor modifies the dynamics on a certain channel. And if we had a full joint model over all the x's, that would be much more difficult. So certainly it's a kind of pragmatic choice which relates to our application. So basically we're just using AR models here, conditional on and so this can be put in the general Kalman filter framework, just of course by stacking the state of the last p observations into the state that we see. The other thing is that, okay, we've got a switching Kalman filter. You might think, well, you have to run EM, forward, backward stuff in order to make this work, in order to do the learning. But bear in mind that we have some clinicians who actually are able to mark up data for us. So, for example, we may know things like this, that there's a bradycardia, this is the heart rate's dropping here. So in this situation, we can say, okay, this section of data, really we need to learn, and say this is the heart rate channel here, then we really want to learn AR or ARMA or REMA model for this data, and then under this switch setting, when the bradycardia is active, then basically we have some marked up data. So it's actually easy to learn the parameters. We can just learn them like that, rather than have to do it by, say, EM or something like that. So that really actually helps the building of this model. Another example is that, fairly simple example, this one's with temperature. If we had some, say, temperature of this is the monitoring of the temperature, this is at 37, I think that's the correct temperature for a human. Yep. And okay, and basically what could happen is that if this probe if it fell off, we'd expect this to kind of decay back to the incubator temperature, which is like this. And so what happens here is that basically we expect to see here through sort of Newton's laws of cooling, we expect to see an exponential decay, which we can model with an AR1 process. So basically, one can build different kinds of models for those different situations where the factors are active. And we notice, for example, that if we say that, oh, the temperature probe, the core temperature probe has become disconnected, of course, that will affect the dynamics on the model for the core temperature, but not for the other channels, right? So again, this structure of how these different factors affect the different variables here is actually very important in order to make this thing buildable. One of the other things that we also need to do, and this is pretty crucial as well, is really to understand what normality is. For a particular baby, we've got some different, so if we have some region of data where we have a particular dynamics in, say, the stable situation where, i.e. clinicians are not worried about the baby, they think, okay, it's just going along okay. We can look at this kind of data and actually then model it. And basically what we're using here is an ARIMA model. So if you're not so familiar with this, the I is for integrated. It means basically that a difference series would be an ARMA model, which means that we can allow for drifts to go on. And that kind of thing can certainly happen in our traces. That's why we need this kind of model. So we can actually use these kinds of, but this is fairly standard sort of time series modeling for each of these individual channels and also for the factor settings. So that's the kind of model we're using, say, for the heart rate data. That's the model, and I've told you how to do inference. Let me give you a quick demo of things in action. If I can make this work. Oh, please disappear. Okay. Okay, yep, good. Okay. Right. So what you're seeing here is there's a bunch of traces here. There's a heart rate. Here, the systolic and diastolic blood pressures. I'm afraid the resizing of the screen that goes on when you connect it to the projector means it's got a bit messed up. But basically, some things that you can see in this data are you can see these characteristic ramps here in the blood pressures and this dropout of the heart rate, which is a really strong signal for artifact of taking a blood sample. And also we can see these drops in the heart rate here and here. And this is the ground truth annotation that's provided by clinicians. And basically what we're doing is that we're doing actually a sort of cross-validation setting where we're, say, splitting our data into, say, 3 portions, training on 2 of them and testing on the other 1/3, and then rotating that around. So these are actually the predictions from our system on these different traces. So we can see actually again that it actually has picked up fairly well what's going on in these traces. It's perhaps a relatively simple example, but it's good that it's actually working okay. Okay, let me go back to this. Okay, any questions so far? Happy? Okay, let's just talk a bit more about these inference results. There's some interesting things that can happen here. So, for example, if this is heart rate and this is the humidity in the incubator, and that humidity is actually a good indicator of whether the incubator is open or not, then down here, when there's a drop in the heart rate, that's flagged up as a bradycardia, a drop in heart rate. However, when there's instabilities in these traces later on, but when the humidity is low, actually basically what's happening is that when when the incubator is open and the nursing interventions, we expect these traces to actually be much more variable. And so, in fact, this kind of drop in the heart rate here is actually explained away. It says, okay, I know the incubator is open. In that situation, these traces tend to go crazy, so I'm not going to flag this as a bradycardia there. So just the kinds of things that you'd expect, essentially, from a sort of probabilistic expert system are the kind of things that are happening here. And there are other examples. The sort of thing that you'd expect to happen, that when you see an artifact going on in the systolic and diastolic blood pressure due to the blood sample, basically you'd expect that the state for, say, the blood pressure here would actually evolve under the system dynamics. Is just free running. We're not making observations of it now, and in fact, so then you'd expect, you know, these error bars to kind of blow up and this thing just to go up to some, it sort of doesn't know what's going on. But when this thing finishes, then these things collapse again. So just the nice things that you'd expect to happen in this kind of model do actually happen. It's perhaps worth saying at this stage that actually the reason that we need that artifactual state for the X state that I talked about at the beginning is that when the blood, say for example this blood sample factor is inactive, then the artifactual, say the systolic blood pressure, this channel here, the artifactual thing is just cloned to the physiological blood pressure. But what happens is that when this factor becomes active, we know that we're going to start to see this ramp occurring. So basically then, once that factor becomes active, the artifactual model starts ramping, and it actually sort of expects to see this kind of behavior in these blood pressures, whereas there's the true, the uncorrupted channel actually just continues free running and not getting any observations. So yeah, there's some details of how this is all built in order to make these things happen. We can do some evaluation of this kind of model. What I can talk about is, okay, as I said, threefold cross-validation of 360 hours of monitoring data. Our model, we can compare the Gaussian sum approximation, a Rao-Blackwell particle filter, and also a sort of simplified model. Rather than using a factorial switching Kalman filter, we could actually use a factorial HMM. This is a much more pleasant model to compute with. We can actually compute very efficiently with that. However, unfortunately, it doesn't actually model the data so well. I'll show you why in a minute. The other thing, of course, is that with a particle filter, we've got this choice of the number of particles. Here we're actually using we're using the number of particles to give us the same amount of computation as we used in the Gaussian sum, but certainly we would expect to be able to improve those results by increasing the number of particles. So kinds of ROC curves we get here. Okay, in these pictures, this is sensitivity, and this is 1 minus specificity. This is the Gaussian sum in the solid line, the Rao-Blackwell particle filter in the dashed line, and the FHMM in the dotted line, which may be hard to see. Basically, what we can see, and as you remember, in our ROC curve, it's good to be up in this top left corner. So we're getting some results, and basically we usually see that the Gaussian sum approximations are more effective, at least in comparison to the Rao-Blackwell particle filter. At least it's more cost effective for the same amount of computation, and for the FHMM it's doing better. An example of that is that if we take the factorial switching Kalman filter, one of the things that it can happen, as we said, the model for normality is that it can allow for drifts, and so we could be happily going along at some heart rate. And if we'd built something like a hidden Markov model, it says, okay, when things are normal, I expect to see a heart rate of about this. Basically, here, there's a bradycardia, and then after that, we go back to a rather different heart rate level. If we just had a simple model that's expected normality to be this and couldn't allow for drifts, then we would actually get rather messed up inferences here, so we might think that this is still some kind of bradycardia that's happening. So we found that the the linear dynamical system actually allowed us to do better than this, just a simple model, the simple FHMM. Okay, that's not doing too badly on time, but there's a problem which we alerted to earlier, which is that, okay, we've modeled maybe of order 10 different factors there, but there are an awful lot of things that can go wrong with people. And it would be hard to model all of those things. I mean, it's really useful to be able to handle regimes that we don't know about. The way that we want to do that is to use this high-tech thing called the X factor, and I gather there's some TV program, but I don't know about that. Okay, so in other words, and this might also be in Donald Rumsfeld's words, this is known unknowns. Okay, it's things that we know. There are things that we don't know about, and how do we deal with those? Well, in static data, a simple way to deal with sort of outliers is basically, say, to take your model of expectation and just kind of inflate the variance of that to make a kind of, I call this kind of a crud catcher model. Okay, you might sort of expand this variance, and then basically, if you've got a mixture between the normal regime in solid and the dashed regime for the abnormal mode, when we see extreme events out here, then basically they'll be picked up by this inflated outlier model. So basically, the challenge is that in static data, it's fairly easy to understand how to model outliers. And even if you have some other known regimes like these ones in green, we have this sort of normality. This is the thing if there's nothing wrong, and then maybe there's also some specific modes when there are certain kinds of problems occurring. Basically, as long as we can still use our broad variance Gaussian to pick up, or our broad variance, our sort of expanded model in order to pick up these outliers. The question is, how do you do that in time series? Well, the way that we've done it actually is to take the standard system dynamics and kind of inflate this system parameter here. Let me see if I've got a slide on this. Yeah. Okay. So what that means is that actually by having a psi here greater than 1, we're actually driving the linear dynamical system with higher amplitude noise, and that means essentially we're putting more power into the system. So if you look at the power spectrum for this linear dynamical system, will have some power spectrum, and because we're using this trick of stacking the state, it could correspond to, say, something like an AR5 process. If we just look at the power spectrum with, say, psi is equal to 1, the standard thing is like this. Basically, if we increase the noise covariance on the driving system model, it's going to actually put more power in all frequency components. And basically, remember that if we have something like an AR process, it's basically just a Gaussian process. Its eigenfunctions, it's a stationary Gaussian process. Its eigenfunctions are sines and cosines, and basically what's happening is that we're doing the exact dynamic analog of increasing the variance everywhere. Basically, we're saying that all modes will actually have an increased variance relative to the normal mode. So it's the dynamic analog of the 1D case. So let me give you a demo of the X factor in operation. I need to get back this. Yep. Okay, so again, we've got some data with heart rate, blood pressure, and so on. And here's your favorite blood sample happening here. And here is some sort of unexplained variation. So basically what's going to happen as we come through here on the model, will pick up these things like this. Okay, so this This is the true, as it were, so marked up by clinicians. This is some region of instability which isn't attributable to one of these known factors. This is attributable to a blood sample. So what we saw is that this is filled up and this has picked up the X factor here. So we've been able to capture this unexplained variability with the X factor. Okay, let me just give a little bit more demonstration of this. We can also look at, say, from other examples where we'll see some unexplained variability, say in these oxygen and blood pressure traces. It's picked up in the X factors, and similarly in this data here. There's some details here about, one thing is that we need to actually set this inflation factor, this psi, and that is one place where we actually have used EM, because basically we have some knowledge about those regimes where we can actually get the X factors happening, but basically we can actually do this by running EM. So let me just conclude by saying that, I guess in contrast to quite a lot of work we've heard about it earlier, we're trying to address a fairly complex physiological monitoring data. One important thing that we've done in order to address this is actually to deal with this problem of structuring the relationship or the knowledge about how having this factorial state, or this factored state, how that actually affects the underlying dynamics, these linear dynamical systems, and also how the observations are affected. So the fact that there is interpretable structure here has actually allowed us to build this system, which is in some ways a combination of knowledge engineering about how all these interactions occur, added to some general learning techniques for learning these linear dynamical systems conditional on the switching states. We've also shown how this can be applied to novel situations when we have these unknown regimes that we need to handle. And of course, although this has been applied to neonatal intensive care monitoring, I think these kind of techniques are actually much more generally applicable to a wide range of condition monitoring problems. And if you want to learn a bit more about that, then here are some references. Okay, thanks.
The outlier detection thing. So I didn't quite get the analogy. So in the univariate thing where you have a big variance, the data is a point, and if it lies far away, it's in the tails.
Right.
But in your case, isn't the region you're in, it's a distribution, and is that analogous?
Right. Okay, let me see if I can do better at explaining this. If we have, say, some time series of length n or something like this, what we're saying is that think of that as an n-dimensional point, and think of say an AR model as being a big multivariate Gaussian. Okay, it's in this case an n-dimensional multivariate Gaussian. What we're saying is that basically by inflating the system noise, basically if we took the kind of hyperellipsoid that corresponded to that Gaussian, what we've done is just blown up along all the dimensions, right? And so then it is actually analogous to the sort of 1D picture that I drew. But yeah, okay, sorry.
This Gaussian sum approximation, is there actually a collapse back to a single Gaussian, or do you carry more complex statistics? I didn't quite understand.
Right. Okay. So I think the simplest thing I do here is that I admit some ignorance on this. But as far as I recall, I think it's just collapsing back to a single Gaussian. You can certainly do things where you kind of fit mixture distributions to these
And
things.
it worked
People have
better
done
than
those.
the Kalman, than the particle filter.
Well, okay, it worked better given the amount of particles that we were using. It's clear that by increasing the number of particles, you should be able to do better. And in fact, it would make sense to run with a lot of particles to sort of untangle the question of what's going on with the approximations and what's going on with the model. You know, how good is the model, and how much of that is due to approximate kind of inference in that model. So, yeah. Mike.
I think in the original paper they take say a pair of Gaussians that are close together and merge them into one and play around with it that way. We don't, in the paper they don't collapse them back to one.
Okay. I think that certainly what we're doing is collapsing them back to one, as far as I recall. But they're clearly, certainly in Weston Harrison's book, there's some discussion of these kind of models and various kinds of things that you could do. Steve.
Just going to point out there's a lot of work in the sensor and tracking literature under the kind of name of covariance union for trying to make what were various disparate multiple hypotheses that come from, in effect, factorial Kalman filters into a single Gaussian predictive distribution, so you can keep iterating your good old Kalman filter.
Sure.
And that's not quite, it's sort of a little bit flaky on the statistics, but it actually works tremendously well. Sadly, better than more mathematically profound approaches.
Such is life. Okay.
Yeah.
Okay. Okay.
Is the system implemented in a real scenario, or are you testing it on?
That's a good question. Certainly, the system is developed for John's PhD thesis. It was in a sort of offline canned data method. Although it's worth saying that I think one of the things that was actually very important to actually make this as effective as it has been is the fact that John was actually had a desk in the hospital and actually worked with the people there. To understand this kind of structure, even though there's a clinical fellow who was working with us on this, it was kind of important for John to be embedded in the hospital to actually understand really what was going on with the data. Okay, to answer your question, what we're doing right now is actually doing a sort of more realistic test where, okay, you actually have to understand how neonatal intensive care units work. They work on 12-hour shifts. What we want to do is to take data from, say, 9 hours, process it, and as you can see, this is faster than real time, process it, and then flag up possible annotations to our clinician and say, okay, can you go and find out what happened, at 3 a.m. in the morning or something like this? Because basically, once the shift goes off, then nobody can really remember the exact details. I'm sure there's some records in the files, but if you have some specific queries, it's hard to do. So basically, we are moving to something that's a much more sort of real-time kind of evaluation. We're not moving right now to sort of cot-side monitoring, like that could come later, but certainly we want to get nearer to the clinical context.
Well, then let's thank the speaker again.